Hello everyone. So in this video I'm going to give you some details on two-dimensional motion which I think are not really covered that well in the book. I think the best time to watch this video is after you've done the reading 3.1 and 3.2, but before you look in detail at the example 3.1. I think that this is going to help you understand example 3.1 better. So the first thing I'd like to do is I wrote down the two equations in the book, 3.8 and 3.9. These are now vector equations for the velocity and the position of an object. Notice how the book is writing I's and F's to be initial and final positions, initial and final velocities. We have the time and we have the acceleration here. I'm going to do a simple rewriting which I think is a little bit more clear to show which things change with time and which things are constant with time. Okay, so this is what I mean. When I write the velocity and position, I normally write the vector part is the same, but I write on the left side of the equation v as a function of t and r as a function of t. That clearly states that this velocity is changing throughout the entire path of the object, and the position is also changing. The r0s, or r0s, and v0s, those are the initial position and velocity of the object. These things do not change. For a given motion, when I throw a ball, the position and velocity are always the same, but the current position and current velocity specified by what time I'm asking about, those change. So both of these are correct ways of writing equation 3.8 and 3.9. These are called the kinematic equations. I guess the book hasn't really been very clear about calling them that, but these are called the kinematic equations. Kinematic means something like how can things move. It's not why they move, but it describes how they can move. So either one of these forms is correct. I'm just giving them to you because I will normally write them like this. So the other thing I want to talk about is going to help you understand example 3.1. It's also something that some people have noticed already doing whiteboards, but that when we write one vector equation, there's more information in here than you would think that one equation can give you. Specifically what I mean. When we have one vector equation, that really means that we have two scalar equations. The 2 here is, of course, because we're in 2 dimensions, x and y, in the x and y plane. If we were in 3 dimensions or 4 dimensions, this would be 3 or 4. So people noticed this when they were doing whiteboards and they had an equation like this, a plus b equals c as vectors. They noticed that this was the same as having two equations, the x component of the a vector plus the b component, the x component of the b vector plus the x component of the c vector, and the y component of the a vector plus the y component of the b vector plus the y component of the c vector. So essentially what you do is you can turn a vector equation into two scalar equations just by putting the same component, each of those things, and then they just drop right out. And this is actually what you're going to be using for the most part to solve problems. So how does this work in practice? Well, let's rewrite the velocity equation up here in this manner. That's pretty easy to do. First we have Vx as a function of t equals the initial velocity in the x direction plus the acceleration in the x direction times the time. And then we have the velocity in the y direction as a function of time equals the initial velocity in the y direction plus the acceleration in the y direction times time. So of course time doesn't have a direction, time is a scalar, so you don't, and also that's notated up here, there's no arrow on time, so there's no x and y on these t's, whereas there are arrows here, and so you get x and y there. So in general, we'll have velocity and accelerations that are in multiple directions, and you need to split your single vector equation up into these. Okay, so now with all this information, I think that example 3.1 is going to make a little bit more sense to you. On a side note, when I first learned about this, that, okay, we have, when I learned about this kinematic equation, this velocity, saying, oh, we can find the velocity, we can find the position along the x direction, when I first learned that the two directions, the x and y, were totally separate, not connected at all, I basically didn't believe it. I remember as a student thinking that this was some kind of amazing thing that somehow motion in one direction didn't change the motion in the other direction. It actually took me a little bit while to sort of wrap my head around it. But remember, it's because that the equation is given right here, and the equation is as a vector. And because vector, the components of a vector has to satisfy the same equation as the vector itself, that's where this comes from. And so practice is the best way to convince yourself that this is true. And so we'll do some whiteboards on that.